This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
Welcome back to the WE-Heraeus International Winter School on Gravity and Light. Today's sheet is the first actual physics sheet of this school, so we'll deal with the Schwarzschild spacetime. In exercise 1 we will look at the geodesics in a Schwarzschild spacetime. So we consider a manifold equipped with a so-called Schwarzschild metric that is given here. In the following we will use this notation, the shorthand notation, and the first question now is to write down the Lagrangian. So, Lagrangian in its abstract formulation is given by GAB gamma dot A gamma dot B. For this easy case of a Schwarzschild metric, this becomes the Lagrangian L is equal to 1 minus 2 Gm divided by R T prime squared minus 1 over 1 minus 2 Gm by R x, not x, but R prime squared minus R squared theta prime squared minus R squared sine squared theta phi prime squared. This was already the answer to the first question, and we move on to the second question. So there it starts with a little remark that this Lagrangian can be parametrized by lambda, which we will see is just the eigentime, in such a way that the Lagrangian is equal to 1 for all lambda. Now there are 4 Euler-Lagrange equations for this Lagrangian. We want to derive one of them, namely this one with respect to the function t of lambda. So the Euler-Lagrange equation is 0 is dl by dt prime. This one derived again by prime, so the prime always indicates derivatives with respect to this parameter lambda. And the second term is a del L by del T. So we see that the Lagrangian, which we just wrote down, does not depend on T itself. So del L by del T is 0. However, it is dependent on T prime. So we can derive del L by del T prime is just 2 times 1 minus 2 Gm divided by R T prime. And this expression, again derived with respect to lambda, gives just 2 times 1 minus 2 Gm divided by R G double prime plus 4 Gm divided by R squared R prime T prime. And this is already equal to 0. So we can rewrite this equation as T double prime plus 2 Gm divided by R squared and 1 minus 2 Gm over R of R prime G prime is 0. So here we see that we could read off the Christoffel symbols for the Schwarzschild metric in the case that, so this is gamma, so this is 2 times gamma of T R T, and of course is equal to 2 times gamma T G R. However, we don't want to go further into these Christoffel symbols, but we rather would like to show now that the Lie derivative of G with respect to the vector field kt, which is just given by del t, vanishes. So we just take the Lie derivative GAB, so take the Lie derivative with respect to the vector field kt of G and evaluate at the components A and B. This is equal to kt acting on GAB minus, no, actually it's a plus here, GMB and the del t acting on, no, that is, well, that is correct, but not del t, but del xa acting on the mth component of kt, and this goes also the other way around, so we take del xb acting on the mth component of k. So in this term we see that this is the derivative of G with respect to the function t. However, we know that our Schwarzschild metric does not depend on does not depend explicitly on time, on a time function, so this will give 0. And we also know that the components kt 0 is 1, while kt 1, 2 and 3 are all 0. So what we do here, we derive a constant, well, that certainly gives 0, so this term goes out, this term goes out, this term goes out as well, so all this is 0. So we showed that the Lie derivative of G with respect to the vector field kt vanishes. So what does this mean? Well, we have some kind of symmetry here. And of course we see that these symmetries with respect to time translations, well, this gives rise to conserved energy. And the last part of this section here is to find the conserved quantity. So the explicit form is given by this expression here. And now we want to derive an expression for this quantity t prime appearing in the Lagrangian. So we see we have kt here, but with an index down. But that's not a problem. So we see that kt index down xa prime of lambda is a constant. However, we're only given the kt with components up. Well, that's not a problem. We just take GAB, ktb, xa prime of lambda, and this only gives us contributions, since the only contribution here from the kt is for b equals 0, which then also sets a to 0 due to the special form of our Schwarzschild metric. So we have that this is g0, 0 times kt 0 times t prime of lambda. This is just 1 minus 2 gm divided by r g prime of lambda, and this is constant. And now we write this constant as the square root of some E, which will later turn out to be the energy. So, and then we find that t prime of lambda can be rewritten as the square root of E divided by 1 minus 2 gm divided by r. This was the first part of this exercise. Now we see that also this metric fulfills so-called spherical symmetry. That is the Lie derivative of g with respect to these vector fields, which we already know from the last tutorial, that the Lie derivative vanishes. So which physical quantity is conserved by this symmetry? Well, that's rather easy, since we know that this is just, so in quantum mechanics, this would be the algebra for angular momentum, and indeed angular momentum is conserved here. And to fix angular momentum we need two vector fields that fix direction, and one vector field that fixes the absolute value of angular momentum. So the first two of these vector fields, x1 and x2, they fix the motion to a plane of constant theta. And if we have found such a plane of constant theta, we can of course turn our system of reference in such a way that we end up at theta is equal to pi half, which makes life much easier, since then all the sine squared or sine theta that appear are just 1, and we don't need to carry them through anymore. We just can set them to 1. And of course we can always turn our system of reference such a way that if we have fixed ourselves to a plane of constant theta, so that we can turn around our system of reference to theta is equal to pi half. But how can we now derive an expression for the remaining term, phi prime of lambda? Well, that's not a problem. We already saw how to derive the conserved quantity for a symmetry on the last exercise, or in the last question. So we recall that we need x3 indexed down, x prime xa prime of lambda is constant. We can rewrite this to gab x3 with index b up now, and the xa prime of lambda is constant. So now we can take, okay, x3 only, which was exactly del by del phi, has only a non-vanishing b equal 3 component, which then means we get that g33 x3b and phi prime of lambda is constant, and this constant we like to call minus j. So which will turn out to be the angular momentum. So g33 was just minus r squared sinus squared theta. However, we know that theta is equal to pi half, and thus the sine squared is just 1. And for that we find that phi prime of lambda is equal to j over r squared, which is a nice formula in fact. And now we are prepared to look at the Lagrangian again. So we now use the fact that the Lagrangian is equal to 1 over the whole parametrization. So the Lagrangian itself is a conserved quantity. And now we want to insert all the previously obtained results, and then we'll see what we get out. So we have 1 is equal to the Lagrangian is equal to 1 minus 2 gm divided by r, and now we insert t prime, so this is just e divided by 1 minus 2 gm over r squared. We get a minus sign, a 1 divided by 1 minus 2 gm over r prime squared. We can't substitute anything in here since we have no conserved quantity for r prime. However, in the next term, which would be theta prime, we know that this term vanishes since we have our motion in a plane of constant theta. And the last term contained phi prime. Well, we just found a formula how to replace this phi prime by j squared. So phi prime squared is just j squared over r to the 4th power. And now we substitute all the terms and can put them all together, and we will find that 1 is equal to e or divided by 1 minus 2 gm over r minus 1 over 1 minus 2 gm divided by r prime squared minus j squared divided by r squared. And now we put all terms that contain e, which is only the first one here, to one side, and all the other ones to the other side. So we find that this is e is equal to 1 minus 2 gm divided by r times 1 plus j squared divided by r squared plus an r prime squared term. So the result will be that e is equal to r prime squared plus 1 minus 2 gm divided by r plus j squared divided by r squared, and the last term minus 2 gm j squared divided by r to the power of 3. And now the last question asks us to interpret the terms that appear in this expression. So on the left side, this is the total energy E. So we know that quite well. R prime squared, well, that is just some kind of kinetic term. So we have not introduced a mass here, so we have unit mass m equals to 1. Then this term here, the 1, is just the mass term. So the relativistic correct mass term, which would be mc squared. However, we set both m and c to 1, so we just get the 1 here. Now we have minus 2 gm divided by r. Well, you should know that. This is just the Newtonian gravitational potential. The next term, j squared divided by r squared, well, this is just a contribution due to the angular momentum. That is also quite standard. But now this last term here, this is the interesting one. And this one then indeed turns out to be the correction term from GR. And you see, this is divided, so you have constants here in the numerator, and in the denominator you have an r to the power of 3. So this term will contribute when r is small, and that indeed is, of course, the physical relevance of Schwarzschild spacetime. You don't, far away from the black, for example, the black hole, you don't see much effects that are different from the usual ones, so usual classical picture. However, if you go near the black hole, of course, the motion of your particle on the curved space there is quite different. And there, this term gives us the correct equations. So we see we can interpret all these terms, all the 4 terms here are purely classical. A kinetic term, a mass term, the classical gravitational potential and contribution of angular momentum, but only the last one really says, okay, this is the correction to the motion that comes from GR and corrects our classical motion. So this is the first exercise of this sheet, and there will be one more exercise which will deal with gravitational redshift. Also an important effect appearing in general relativity. So we consider a spacetime that is equipped with a Schwarzschild metric as well as 2 observers, 1 and 2, that are at rest in their respective system of reference. That means their coordinates r, theta and phi, they don't change. They only move in time. The observers sit at the same theta and phi for simplicity, while the radial coordinates r1 and r is smaller than r2. So we want to derive first an expression for t prime using the Lagrangian from the previous exercise. So we remember we have that the Lagrangian is equal to 1, and the first contribution was 1 minus 2gm divided by r t prime squared. Now there would be more terms having r prime, theta prime and phi prime. However, we know since the observers don't move, well, these terms get kicked out. So this is indeed the whole expression we need to look at here, and this means that t prime is equal to 1 over square root of 1 minus 2gm divided by r. Now observer 1 emits photons that observer 2 detects. The gap between 2 photon emissions is delta lambda 1. So what this means is, in physical terms, observer 1 emits photons, and between 2 photo emissions you have the interval delta lambda 1 in eigentime. So observer 1 emits after each period delta lambda 1 a photon. However, observer 2 maybe sees this length differently, and we want to calculate this. So, of course, there our formula for t prime derived in the first question will prove useful. We see for fixed r, we have a fixed r here, so the whole right side does not depend on lambda. So we can just integrate this, and we will find that delta t, so in the coordinate time, that this is just, so for observer 1, this is 1 over square root of 1 minus 2gm divided by r1 delta lambda 1. And of course, for observer 2, this is delta t2. This is just 1 over square root of 1 minus 2gm divided by r2 delta lambda 2. So now we have to consider these two, delta t1 and delta t2. So both distances in coordinate type, and therefore it's best if we draw a spacetime diagram of this whole situation. So we have up here is the time, and here we say that there goes the radial coordinate. So we have observer 1 sitting at R1, observer 2 sitting at R2, and the world line, it looks just like that as the coordinates in space, so r, theta and phi never change. This is the world line of these two these are the world lines of both observers. Now, observer 1 emits a photon here and a photon here. So this is delta T1. So, and now we see, okay, this goes some way, for example this way, all the way here, where observer 2 detects this photon. And now we wonder, how does this path, or how does the world line of the photon look like if it is emitted up here? And now we use our knowledge from the first exercise. We know that the Schwarzschild spacetime has a symmetry with respect to time translations. Since the vector field kt, which was just del by del t, was a killing vector field. So we know that the situation from here, from the first emission to the second, didn't change but for a constant offset delta t1 in coordinate time. But on r or something else, nothing has changed on the other coordinates. So the situation up here is just the same, and we get just the same curve parallel up here to the second detection by observer 2. So these two lines can be said to be parallel. So their distance, the distance between 2 points of equal r, is always the same as delta t1. But you know also that this here is delta t2. Well, but if this holds here for that the distance in space-time between every 2 points here that have the same r is always delta t1, well then delta t1 is obviously equal to delta t2. Okay, this is good. We find that delta lambda 2 then is just... no, we have to write it a little differently. So we just say that this is delta lambda 1, which will prove easier in the next exercise if we do it this way, that this is exactly big square root 1 minus 2 gm divided by r1 over 1 minus 2 gm divided by r2. And this is times delta lambda 2. So you get this fact. So the emission, so so observer 1 emits photons with a delay of in its eigentime of delta lambda 1. However, observer 2 detects these with this factor here. So he picks up such a factor here. And now we look, how does this look at the frequency level? So consider the ratio of the frequencies omega 2 divided by omega 1. Well, it's quite obvious to see that this just corresponds to the case that delta lambda 1 is divided by delta lambda 2. Well, that is easy. This is just this big square root we have here. This is 1 minus 2 gm divided by r1 divided by 1 minus 2 gm divided by r2. And indeed, since we have R1 is smaller than R2, we see that the numerator up here is smaller than the denominator, so this will be smaller than 1, which corresponds to omega 2 being smaller than omega 1, or for wavelength, we know that the observed wavelength for observer 2 is so I call the wavelength here not lambda, since lambda is already given, but we will call it, well, we'll call it just mu. We then know that the wavelength observed by observer 2, mu2, is larger than mu1. Well, and larger wavelength, we always call that this is more red. So we have a redshift. Now we look at what happens if observer 2 is being approximately at infinity. Well, observer 2 being approximately at infinity for a Schwarzschild spacetime means that he is sitting in the approximately flat space. So we can just take the limit of this expression for small r2, well then the denominator just kicks out here, and we find that omega 2 by omega 1 for r2 to infinity is just square root of 1 minus 2 gm divided by r1. And now the second special case is what happens if we send r1 to the Schwarzschild radius. Rs is 2 gm. But you see that then the numerator becomes very, very little. So the observed frequencies, so omega 2 grows larger and larger the more R1 is near the Schwarzschild radius. And of course, if we are exactly at, so the redshift is even stronger and stronger. So the wavelengths are, so you observe very, very large wavelengths, and if you go to the Schwarzschild radius, so if you sit now exactly at the Schwarzschild radius, this whole formula then breaks down. You can't observe a frequency then anymore, so you can't observe any wavelength, and so you can't bring information from the Schwarzschild radius or even from below the Schwarzschild radius outside. This is not possible. You have to sit above the Schwarzschild radius. And with this, we want to close this tutorial, and we hope to see you next time.